The eLife podcast from eLife, the open access journal for outstanding research in the life and biomedical sciences. Online at elifesciences.org.
Hello, welcome to episode 34 of the eLife podcast, which is produced by The Naked Scientists. I'm Chris Smith. This month, stem cells for septic shock. But will they work? Why flies doze off like we do after a big meal, and new insights into how ants navigate. At first, though, we're stepping back millions of years into mankind's past. Marco Cherin.
We discovered new human-like footprints dated at about 3.66 million years in the known site of Laetoli in northern Tanzania. Laetoli is one of the most important paleoanthropological sites in the world for two reasons. One is because of the discovery in the 70s of some very well-preserved fossils of human ancestors, Australopithecus afarensis, the same species as the famous Lucy. The second reason is the discovery of the earliest human-like footprints in the world, dated at 3.66 million years.
And you've now found more of the same?
Yes. The first set of footprints was discovered in 1978 by Mary Leakey. Mary Leakey's discovery composed three different individuals walking in the same direction. We discovered just 1.5 years ago two more individuals walking on the same surface.
First of all, just set the scene for us and tell us what the Laetoli site where you've been working looks like to an observer.
The Laetoli site today looks like African savanna. It is included within one of the most amazing protected areas in the world, the Ngorongoro Conservation Area. But today, this is really a rough place, rich in dust and acacia trees and bushes and shrubs. But sometimes in this savanna environment, a very, very peculiar rock can outcrop. And this rock is a hard volcanic ash in which the footprints were preserved.
So these individuals, whoever they were, went walking across some freshly fallen dust from a volcano, left these impressions behind. How did they then get preserved so that you could come along 3.66 million years later and dig them up?
The preservation of fossil footprints is very rare. In that case, a near volcano was erupting several times in a few days. The ground was completely covered by this fine ash. But the other and fundamental thing is that we were in the beginning of the rain season. Some rain fell down on the ground. The ground was soft. Hominids and other animals were walking on this soft surface, leaving their tracks. Immediately after the passage of these creatures, another volcanic eruption covered the surface with new ash.
And how did you come to stumble upon these tracks that these extremely famous people managed to not find 30 or 40 years ago?
The tracks were discovered by our Tanzanian colleagues who were working in the Laetoli area for a landscape impact assessment, because the Tanzanian government wanted to build a new field museum, to bring tourists to have a look. So Professor Masao were digging 50 or 60 test pits to evaluate the possible impact of this new building. And during these digging activities, he discovered the new printed surface.
And when you look at these footprints, what can they tell you about the individuals that made them? Because one thing we know, if we look at humans who walk on the beach,
Yes.
we can tell
Yes.
quite a bit about the size, stature, speed, and so on of movement of the
Yeah.
person who leaves footprints behind. So what can we learn about these ancestors of ours who left the footprints?
Footprints are very interesting tools in paleontology because they can tell you much more things than simple bones. In our case, the human-like footprints from Laetoli, we can say that they were part of the same social group because the footprints were printed exactly on the same geological layer. The second thing is about the pattern of locomotion was not so different from Homo sapiens, our own species. So this is a very interesting evidence of functional bipedalism in very, very ancient hominids.
What about the potential size, the proportions of the
Okay,
individuals that
yeah.
made them? What can you learn about that?
We were really, really shocked when we cleaned the new trackway because it is composed by very, very long footprints. So we can expect that the owner of this feet was a tall individual. And we found that one of our new individuals could reach the stature of something like 1.65, 1.7 meters, comparable to modern humans. Normally, we thought that these ancient human ancestors were tiny creatures. For the first time, we have sure, independent evidence of the occurrence of individuals with very high stature. And in the same site, we have individuals with different size. And this is one of the most important novelty of this work. We have tall individuals and we have also tiny individuals for the first time in the same place at the same age.
So one giant leap for humankind. That was Marco Cerin. He's at the University of Perugia in Italy. Clinical trials are usually based on findings from animal studies, but it turns out that quite a few of these studies are based on dubious methodology, so a comprehensive review of the background literature is absolutely critical, as clinical investigator Manoj Lalu found recently.
Many investigators in the past have looked at individual studies that have been performed in a lab and said, hey, this looks great, let's try this out in patients now. However, that's been met with largely, unfortunately, negative results, meaning most things don't work that way.
Is that not what we call evidence-based medicine?
It is in some ways, but problem is with what we call preclinical work or basic science work, the evidence base is usually pretty small, and you're talking about experiments with 10 to 20 animals. However, in clinical medicine, usually we're talking about evidence that covers thousands of patients.
So you're saying there's a fundamental problem here. People do research on a small group of animals and then call those men, not mice.
Unfortunately, yes, that's usually what occurs. And what we were trying to do is provide an alternative pathway that perhaps people can explore to get things from the bench to the bedside. Basically, we're looking at using stem cells to treat septic shock. So that's when you have a life-threatening infection. When a person has this, their blood pressure gets very low. They get admitted to an intensive care unit. Right now, what we do for these patients is we give them antibiotics, we give them lots of fluids, and then we give them other supportive treatment. And we treat the underlying infection if we can find one as well.
What would be the rationale then for attempting to use stem cells in that sort of setting? How might stem cells assist a doctor making someone with septic shock get better?
We think they might work in several ways. So often people think stem cells go in and they become part of your body. However, in the setting of septic shock, we think these cells go in and they have anti-inflammatory effects. So when you have septic shock, you get really a huge amount of inflammation that occurs in your body. We think these cells decrease the inflammation and allows the body to recover a little bit better that way.
And what did you find when you began to survey the landscape of this subject a bit?
What we did, which was different from what other people have done in the past when they're trying to move from bench to bedside, we looked at the complete literature. So we performed what's called a systematic search to try to find every single study where they had given animals these stem cells. And what we found was overall that these stem cells, when you looked at the broad literature, reduced death in these animal models of septic shock.
And were you happy that those studies that you were looking at had been conducted in a rigorous way, in a way that could be translated to the bedside in an appropriate way rather than in a speculative one?
First of all, I guess on the surface, yes, we're happy that many different labs and many different groups have almost replicated the same sort of results, meaning that they had these animal models of septic shock, and overall, it appears that these cells are protective. On the flip side, which is a little bit concerning, the rigor that you were speaking about there, that's where I think we can improve ourselves as basic scientists in terms of looking at ways that we can reduce what we call bias in our studies.
Is that not something, though, that basic science should be across anyway? Someone who is training to become a professional scientist should understand from the get-go how you do an unbiased, balanced and rigorous study. Otherwise, it's not valid science.
That's a very good point, and I think it speaks to something that we're only recognizing in the last few years, and that's that we don't get this sort of training. And really, when you're looking at these sort of methods to reduce bias, to improve rigor, they're not really taught in a systematic way to trainees.
Would not a cynic put it to you, though, Manoj, that actually what you've done is what you should be doing anyway? Before going anywhere near a patient with any piece of research, we ought to make sure that we have thoroughly appraised the literature so that we make completely evidence-based and informed decisions about anything we do.
I would agree with that cynic and say, yes, this is what we should be doing. However, unfortunately, that's not what's been done in the past. There's a couple of very good examples of this where clinical trials have been designed and the push to move from animal work to patients was around a couple of positive papers. So one was on endothelin receptor antagonists for heart failure, and the second was on an antioxidant agent for stroke. There was what we thought were promising preclinical results. However, the clinical trials ultimately failed, and then retrospectively, scientists went back and looked at the complete literature, and surprisingly what they found was the evidence really wasn't that great when they considered the complete body of literature.
Manoj Laloo, he's at the Ottawa Hospital. You're listening to the eLife podcast with me, Chris Smith. Still to come, how ants get a massive food item through a very small hole, and how diverse is your scientific workplace. Before that, though, whenever you eat a big meal, the chances are you probably feel very sleepy afterwards. This is dubbed the food coma effect, and incredibly, it's also evident even in flies, as Bill Jarr has discovered by filming Drosophila eating foods containing different proportions of nutrients. And studying their brains is revealing a lot about why this probably happens to us too.
It was about 10 years ago now that we first started using these tiny glass straws that we filled with liquid food, sugar water or sugar and yeast solution. And we found that the flies were able to suck food from the straw, sort of like a hamster feeder. And so as you watch the liquid volume go down in the capillary, you could calculate the volume that they consumed. And so by putting these two systems together, the camera for watching them sleep and a second camera for watching these capillaries so that you could constantly monitor how much these flies are eating, we would have a constant readout of food intake and activity and sleep. From this data set, we could see that flies eat a certain number of meals per day. So I simply asked, what does the sleep of these animals look like before and after eating? Is there a difference? We didn't really believe it at first, but then we went through a long series of experiments to try to confirm that what we were seeing was real, that the flies really do sleep more after meals than before, and all of the components of that meal that make postprandial sleep stronger or weaker.
I was going to ask you about that because there is this claim that if over your Thanksgiving table one overconsumes turkey, you're much more likely to feel sleepy than if you have, say, pasta. Now, is this true in your flies? If you vary the composition of what you feed them, so they have, say, a protein-dominated dinner, would this make for a sleepier fly?
Meal size or meal volume strongly induces the food coma effect. But independently, protein and salt intake also do it. And so even if the fly is eating a small meal, if there's a lot of protein or salt in that meal, it will induce just almost as much food coma or sleep as the large meal. And so if this is analogous to what happens in humans and all the same nutritional triggers are the same between flies and people, yes, anecdotally, it would be turkey over cake that would cause food coma.
Now, how does this work? Have you got some insights into what is going on in the fly's body, what its physiological mechanism is for detecting what it's had for dinner, and that then having this sleep effect?
In the gut, there's certainly lots of receptors and different mechanisms for sensing the different nutrients. How those signals are integrated to dictate appetite and satiety or this food coma effect, we're not really sure. The mechanisms that we identified first were all in the brain, and we found a few different circuits close to each other, so we think they form part of a network that regulate this food coma behavior, but only to protein. And so we think that the other circuits that must be used to regulate food coma in response to salt or meal size still have to be found.
So in essence, there is some kind of mechanism for detecting what has been consumed and how much has been consumed. This is being fed onto a certain population, probably a mixed population of cells that are responsive to different micronutrients in the brain, and that is then impacting on sleep and behavior.
Right. And if you look at where these cells are in the brain, a lot of them pointing to regions of the brain that are known sleep centers. And so it makes some sense that that's where we found these circuits.
Now, from an evolutionary point of view, why is it beneficial to have this behavior?
That's a great question. We've been wondering that ourselves for a while. It could be something as simple as digestion. Someone pointed out to me that perhaps protein and salt are limiting nutrients in the wild for flies, or something, nutrients that the flies really prioritize. And so if that's true, and the food coma effect is there to enhance or optimize the efficiency of assimilation or absorption of these rare or prioritized nutrients, maybe that's why the fly has this effect.
Thinking about it from the other direction, if one manipulates those circuits in the brain that you've uncovered that appear to be sensitive to proteins and to salts, if you fiddle with those neuronal circuits, can you shut off this effect, thus proving that they must be doing what you think they're doing?
Yeah, so the tools we use to do this specifically allow us to turn on and off these different circuits in the brain. And so these circuits that we find are responsive to the food coma effect to protein, we could turn them on and off to make the effect stronger or weaker. When you shut off these or silence these neurons that are responsive to protein, feeding protein gave a huge waking response. So it actually suggests that protein induces both wakefulness and sleepiness, and usually the wakefulness part of that is shut down by these leukocynin receptor neurons.
So that's something to think about while you're tucking into your Christmas dinner, isn't it? Bill Jarr there from the Florida Scripps Research Institute. Now, staying with insects, here's a question for you. Let's say you're an ant and you've just found a juicy treat, but it's too big for you to manage alone. So you retrace your steps to your nest and you invite your sisters to come and help you. But the route you took to the treat involved threading your way through several ant-sized tight spots. The food won't fit through there, so even with the help of your nestmates, you still won't get it home. So what do? Well, thanks to Offer Feinemann, who has painstakingly videoed ants solving these problems, we now know that the answer is that you literally go off the beaten track. Everyone chips in an idea regarding what direction you should all walk in, and you pay a little bit less attention than normal to the chemical signals that led you to the treat in the first place.
We were watching ants carrying large things together. So when ants meet some food item that they can't carry alone, they can just team up 10, 20, 30, even more ants, and just haul it to the nest together. And we were looking at this phenomenon, which is very interesting because it gives you the connection between a single ant and the group. You're seeing the single ants pulling whatever, and the group doing what it does, transporting the item.
Now, if you watch what ants do individually, is it the same thing when they're working alone, when they're carrying something small that a single ant can manage, as when a big group of them do it? Or are there different behaviours that go with those two different scenarios?
Yeah, so there is a slightly different behavior. When you have a big object, the first ant to find it, she will trace to the nest and she will recruit other ants, and these ants will come back with her to the item and they can carry it together.
And how do they find their way back to the nest? Do they follow a chemical trail laid down by the ant that first made that journey back and forth?
Exactly. So when we looked at this first ant, we saw like a very fast stop and go motion. I mean, she runs and stops, runs and stops, runs and stops. And actually, when we looked at this from the side, we saw that each time she stops, she puts down her gaster, touches it to the surface, and that's when she lays a small scent mark, like laying pebbles in Hansel and Gretel. And then when the ants come out of the nest, they can follow these scent marks back to the food item. What we actually discovered now is that the ants also use scent marks also in the stage after they start to move the object, when they're navigating the large object home, and then they treat them in a very different way.
Why do they behave differently? Why do they need new scent marks, and how is their behaviour different on that occasion compared with the first occasion?
So actually we filmed the ants and we just from the stop and go motion of the ants, we can deduce where the scent marks were, and we started to pinpoint each and every scent mark that the ants were laying during this movement. They're actually guiding, they're telling the object where to go next. And then we saw something very interesting, that these ants that were trying to guide the object, the food, with their scent marks, were often making mistakes. There is some conflict between the different scales of organization in the group. Here it's very simple. The ants can go through any narrow passage, and maybe the shortest way to the nest, they will mark through there, but the object cannot pass. What we found when we looked at the sum of all these scent marks, actually what works here is this new ant trail that is just made of very short markings by the ants. They just mark the next step to go, not the whole distance to the nest. This is one aspect of it. And the second aspect of it is that the ants that carry don't follow it religiously. If they would follow it religiously, they just get stuck in these narrow corridors.
So are you saying then that the ants which are carrying the load, they are contributing to the scent marks? Sometimes they get it right, sometimes they get it wrong, but equally they don't follow it religiously, so they sometimes follow it wrong too. And this is going to introduce some sort of noise or error signal into the path they take, and that's in some way going to help them to get back with a big load to the nest more efficiently than if they were to just follow the original path laid down.
Right. They know how to navigate. They do it again is by giving very small opinions. They don't give a huge opinion. This is the whole path you should take to the nest. Just this is the next step you should take. And the carrying ants, they listen to it, but partially. They often ignore it. And these two together, they tune the way that the group listens to the individuals. It tunes it just so that they can pass through these complex environments.
Now, obviously, you made the observations by watching in painstaking detail what these ants were doing, but you can speculate on that behaviour, but have you now taken the data and modelled it to say, well, we think that's what's going on, so now let's do some simulations and see if this is genuinely what these ants have evolved to do?
Right, so that's what we did. Actually, we collaborated with another lab in France, and they're a lab that studies distributed computing. And actually, the easiest way to explain the model that we came up with is by an analogy. Imagine that you're driving in some foreign country and it was just hit yesterday by a hurricane. And what this hurricane did was turn the road signs, but not all of the road signs. Like 95% of the road signs are correct. And you want to get from one city to your destination. What would you do? How would you follow these road signs? Most of them are correct. What you have to do, you have to carry dice with you. And each time you reach a junction, you have to throw the dice. And if you get 1 to 5, you follow the road sign as it is. But if you get a 6, you just choose a random direction. And the theory told us that this is optimal. This is the best you can do. And you will reach your destination in almost the fastest time possible. This is completely analogous to what the ants are doing.
Ofer Feinerman, he's at the Weizmann Institute in Israel. Now, to finish this month, it's often claimed that certain groups are underrepresented in the workplace. But what do the numbers say? And in particular, what do they say about science?
So my name is Kenneth Gibbs. I am a program director at the National Institute of General Medical Sciences, which is part of the National Institutes of Health, and I work in the Division of Training, Workforce Development, and Diversity. Broadly within the scientific community, there's been a long-standing challenge about how do we ensure that our scientific community is able to cultivate and utilize talent from as diverse a pool as possible as it relates to gender, race, ethnicity, people with disabilities, etc. So we set out to explore a few different things. Particularly in the United States, there's been a lot of issues around, again, diversity in the scientific research workforce, and because most of scientific research is done in academia, thinking about diversity in the faculty. So I want to do a couple things. One, provide a systematic and quantitative view on what has been happening in our system over the last 35 years or so. And then how do we use that to build a model to simulate where we might want to intervene as a scientific community to ensure that we can enhance diversity in the research workforce and the professoriate specifically. And we were looking in medical school basic science departments, mainly because we had access to a high quality comprehensive data through the double AMC faculty roster.
And what is happening?
As it relates to the talent pool, we see that there's been a really significant increase in the talent pool of scientists from historically underrepresented minority backgrounds. Those would be Black or African American, Hispanic or Latino or Latina, Native American or Alaska Native, compared to their peers from other backgrounds. We call them well-represented backgrounds. And so we see that from 1980 to about 2014, there was a 9-fold increase in the annual number of PhDs from underrepresented minority backgrounds graduating each year, close to 900 a year. Whereas the faculty from underrepresented minority backgrounds, particularly in these basic science departments, only grew at about 2.6-fold, right? And so we see much greater growth for the underrepresented minority PhD pool relative to the assistant professor pool. This is in contrast to what we see for scientists from well-represented backgrounds, where the growth of those two populations is more in line. The next thing that we see is that there's a broad lack of connection between that talent pool and academic hiring. And I think one piece that was pretty striking was that over the last decade, there were close to 6,000 scientists from underrepresented minority backgrounds who got PhDs in the biomedical sciences, but there were 6 fewer assistant professors in these basic science departments. And so we have close to 6,000 PhDs, but we're losing the population of junior faculty who will be the next generation of scientific leaders.
So you're making lots of potential people to step into those posts. None of them are finding places in these institutions in those posts. Why do you think that is?
It's likely multifactorial. There could be differences in terms of the interests of scientists from underrepresented backgrounds versus their well-represented peers. Are there issues in the culture? Are there issues in the climate? Are people not part of the correct social networks? And then once we have people who actually decide to pursue those careers, there's a fair amount of evidence that there are a number of different biases that exist that can influence what happens as it relates to progressing from the talent pool to academic hiring.
Now, what can we actually do to change this? And rather than just guess and then wait another 20 years to see whether or not we made the right choice, are there any ways that we can bring the huge data set that you have access to and some modern technology to bear and try and crack this nut?
Exactly. So I think that's a great question, right? What we have tried to do historically is say, and when a lot of these diversity efforts started, there was really not an adequate talent pool. And so we spent a lot of effort building that talent pool, which we see has been effective. What we've done is say, okay, now let's use some modeling technologies, a system dynamics model, to test 3 approaches. One, let's see if we just need to keep building the talent pool in isolation, if that will get us there. 2, we need to recognize that, the academic career landscape is a bit challenging at the moment. And so maybe it's a function of just a broader labor market stress. Or 3, maybe it is the function of postdoctoral transitions in academic hiring that need to be addressed. And so we use a system dynamics model to test those 3 approaches. And what the model shows us is that the community needs to focus on postdoctoral transitions and academic hiring. And so once we have this great talent pool, which we do have at the PhD level, there needs to be a focus on ensuring these people are in high quality postdocs, that they then transition onto the market and are hired. A large pool in and of itself is not enough, and more faculty jobs in and of themselves are not enough. And I think one thing that was particularly interesting in the model is that we made sure that the system was one in which there was not active discrimination or bias, right? And so even in that case, the model predicts that there's not going to be a substantive change through the year 2080. Even if we had 70% minority PhDs, we still would have less than 10% minority faculty. And so I think it helps us to say that we don't have to have, malice or ill intent to have this kind of disconnect. It's just a system architecture thing that we need to be thinking about more concretely. How do we focus on those postdoctoral transitions and then making sure that the hiring practices are in line to identify and then cultivate this talent?
Would not the people who are getting those jobs at the moment turn around and say, well, I've worked hard too?
Yeah. I think everybody works hard, right? And so the question sometimes is why diversity? And I say, well, why not? Why wouldn't we want the broadest pool of qualified people tackling these tough challenges? What I'm saying, the results are saying that we actually have a large pool of talented and qualified people that for some reason are not making those connections, right? And so we need to be thinking about how do we ensure those connections are being made? And we know that diversity in many respects is critical to scientific excellence, that groups with more diversity tend to ask broader questions, employ a wider variety of approaches, and ultimately go on leading to newer types of innovations. So there's nothing against the people who've gotten those jobs. It's just to say, hey, let's make sure that we have a full and fair competition. And it seems to be at the moment there's some disconnect, which is not allowing us to have as robust a competition as we might want.
Kenny Gibbs from the National Institute of General Medical Sciences. And both congratulations and thanks to Kenny, because he kindly came in while on parental leave to talk to me. That's it for this episode. You've been listening to the eLife podcast, previous editions of which you can find for free on the eLife website. That's at elifesciences.org, or you can subscribe on iTunes. This is a Naked Scientist production. I'm Chris Smith, and you can find out more about what we do on our website at nakedscientist.com. I shall be back with another look inside eLife next month. In the meantime, though, we wish you a very Merry Christmas and a prosperous New Year in 2017. Goodbye.
The eLife podcast from eLife, the open access journal for outstanding research in the life and biomedical sciences. Online at elifesciences.org.